Hello students, I will show you how to use realization theory to identify the model matrices ABD from so-called impulse response matrices. So, assume known impulse response matrices. We are using the symbol HK, and it is equal to the product of the output system matrix D, A in power K minus 1 times B. For a bunch of indices K from 1 and 2, ... and we assume a number L plus J known impulse responses or impulse response matrices. Hence, this means that we have known matrices, impulse response H1 equal to dB, and H2 is then dAB, and so on. And H3 is then dA squared times B, ... up to the last one, HL plus J. From those impulse response matrices, we define two so-called Hankel matrices. The first one is denoted also H in the lecture notes, chapter 225. I'm using a boldface symbol for the Hankel matrix, and I am using a special notation, 1 given L, and a second Hankel matrix, boldface H, 2 given L. I will define those two Hankel matrices, and then the notation will also be clear. And it is a good idea to start to define this one, and also, which also will become clear in a moment. Definitions. The second Hankel matrix, this H2 given L, is a matrix like this, where this index 2 means that we are using the H2 Hankel matrix first in the upper left corner, here, H2, and this index integer L means that we should stack a number of L impulse response matrices above each other with increasing integers. So H3 here then, ... down to H L plus 1 then. And it is named Hankel matrices because of a special structure. And this is a block column because H2 is a matrix. And then the second block column is H3, H4, down to HL plus 2 then. And using all your impulse response matrices up to K equal to L plus J, then you have H L plus J here, and dot 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 H1 or a J plus 1 and H J plus 2 dot 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 here, and like this. I will also illustrate this with an example. And now you see, if L is specified, then L is the number of block rows, and J becomes the number of block columns in the Hankel matrix, from 1 to column 1, column 2, and column J here. And row 1, block row 2, down to block row L. Now we can write up the first Hankel matrix H1L, because this one should have the same number of columns as this one. Then we have H1 given L equal to. Starting this number 1 means that we should use Hankel matrix H1, stacking L of them above each other, H2 down to HLN. And it becomes a Hankel matrix of a special structure where this second column is like this. We here then have H J here, H J plus 1 dot 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 down to, in the lower right corner, the Hankel matrix H L plus J minus 1 then. Like this. You see, those Hankel matrices are related to the so-called controllability matrix and the observability matrix. Like this. So this first Hankel matrix can be seen to be equal to the product of the extended observability matrix OL times CJ. This is the observability matrix and controllability matrix, but it is also defined as extended observability and controllability matrices. And this one is related to the same matrices in the following way. OL times the system matrix A times the controllability matrix. Where OL is the observability matrix. Using D as the first matrix, D times A dot 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 down to D in power of A in L minus 1. This is a matrix of dimension. Remember, D is a M by N matrix. So this one has M rows, and here we have L block rows. So the total number of rows in the observability matrix becomes M times L by N, the system order. And the extended controllability matrix is defined as the matrix here with B and AB like this up to A in J minus 1 times B. Similarly, the dimension of this one, it is a real matrix with dimension. The number of rows in B is n. So the number of rows in this controllability matrix is n, and the number of columns is then equal to R times J. Because R is the number of input variables. Now, we can write up those details also. Now remember, R, the number of input variables in input vector UK. Remember that U is not necessarily control variables in system identification. Any variables which are influencing upon the output, the system, may be measured and stacked in this U. And M is the number of output variables. In YK. And N is the system order, number of states. Same as the system order. At this stage, unknown, so it is a part of the realization theory. Our knowledge is the impulse response matrices stacked in those two Hankel matrices. And we know that those two Hankel matrices is related to the observability and controllability matrices, like this. The dimension of A, we know that A is square n by n, but this system order n is at this stage unknown. Let me take an example. Given some impulse response matrices, say 5, this means that we know H K equal to D A in K minus 1 times B for all A's from 1, 2, up to 5. We, at this stage, also have to choose one of the two indices, either L and J. It is very common that the user are specifying the number L of rows. And choosing, say, L equal to 2 here. Let us write up those two Hankel matrices. Always start with H2 given L, and L is 2. Then we have H2 given 2 then. We start with Hankel matrix H2, H3, and use all 5 impulse response matrices in order to fill out this one. And we have H4. 3. 3 and H4. Have H4 and the last one H5. So here, 2 block rows and 3 columns. So J becomes 3. Then we see, and the first Hankel matrix should have the same number of rows, columns. And remember that this one can be seen to be equal to dA here times B and AB A square times B. It is simply to prove this one, because H2 is DAB. Sorry, I did an error here, remember? I should have A in between those two ones. So multiplying, we know that H2 is DAB, D and A multiplied in all positions here. Go obtain D times AB is this one. D times A times AB is H3, so on. And this is then the observability matrix O2. This one is C3. Can be written as O2 A C3. Now let us, in this example, write up the first Hankel matrix. H1 given 2 then, which is H1, 2 block rows, H2, H3, H3, 4, this. And we know that this one, of course, if we are using the Hankel matrices, we know that H1 is D times B. We can also do it in this way. This is DB, and then DAB in this one, and then DAB here, DA square B, here DA square B, down to dA in third times B, because H4 is D in 4 minus 1, dA3B. And we know that this can be factored as the observability matrix, D over dA, this times the controllability matrix. So this was an example. Now, assuming that the system is both controllable and observable. In system identification and in control theory also, we usually have to assume that the system is controllable. And in system identification, the system should also be observable. So usually we have to assume that at least a part, maybe a small part of the system, is both controllable and observable. So assuming the system is both controllable observable. This means that the rank of the observability matrix is equal to the system order n, and then the system is observable. And if the rank of the controllability matrix is n equal to the system order, then the system is also controllable. So then, by this assumption, we know that rank OL equal to n. And this is the observability matrix. And the number of columns in the observability matrix is equal to the system order n, or n columns. And those columns should be linearly and independent for this to be true. And then the rank of the controllability matrix Cj is also equal to n. Looking at the controllability matrix, the number of rows is n, so there will be n linearly independent rows. Yeah, so this is our knowledge. Realization theory deals with calculations, back calculating to the model matrices A or D, A, B, and back calculating also to the system order n from those two Hankel matrices. Well, definition for a realization theory. Loosely spoken, back. To find system order n and model matrices that is a realization, the system model. So back calculating to the model matrices, say A, B, and D from known Hankel matrices. Have two-one, H1 given L, which was equal to OL Dj, and second Hankel matrix H2 given L, which is equal to the observability matrix OL times A times Cj. This problem was solved as late as in the end of the 1950s in an algorithm published by Ho and Kalman. As I remember, it was back in 1959 or so. But later on, in the 60s, there was published a famous some software for a famous linear algorithm in linear algebra called the singular value decomposition. And remember, this singular value decomposition is the tool to deal with the rank of matrices. So remember, the rank, as I said here, we know because we assume that the system is observable and the system is controllable. Then we know that by assumption that the rank of the observability matrix is n and the rank of the controllability matrix is n. So we know that we don't at this stage know OL and CJ separately, but we know that the rank of them is n. So there exists a lemma also in linear algebra, that the rank of a matrix which is equal to 2 rank n matrices is equal to n. And I hope this seems natural, that the rank of this Hankel matrix H1L is equal to n. Remarks. One remark is that the rank of this first Hankel matrix H1L is equal to n. Because of this lemma also in linear algebra, that the rank of 2 rank n matrices, or the product of 2 rank n matrices, is equal to n. And as I said to you, the singular value decomposition acronym SVD is the tool to deal or calculate rank of matrices, or D rank. The SVD is a decomposition. It's a decomposition method, such that if we calculate the singular value decomposition of this known Hankel matrix H1L, then H1L could be decomposed into the product of 3 matrices separately. U is the left singular vector matrix times a diagonal matrices of singular values times a matrix of right singular vectors, V transpose. Next week, I will introduce the singular value decomposition in more detail. But we have a MATLAB script for calculating USV. The MATLAB script would be like this. U and S and V would be calculated by the SVD function. And the argument is this, say, this Hankel matrix, or another matrix you want to calculate the rank of. And the rank of this matrix is equal to the number of non-zero singular values in this, on the diagonal in this S matrix. Open MATLAB and try. So let me take a few more remarks about this. So here, this remark, the remark that the singular value decomposition is tool to deal or calculate rank. Using SVD we may calculate the extended observability matrix OL and the controllability matrix HJ separately. And remember, when the observability matrix is known, in this remark also N is calculated, the system order. It is actually the rank of this Hankel matrix. In MATLAB we could simply put N equal to rank H1 given L. But remember, as you know from the principal component analysis theory, the rank is not always, due to noise, it is not always very easy to calculate. Actually, you have to investigate the number of non-zero singular values in S. So, remark. Then when we have calculated the observability and controllability matrix, then we may directly find D and B. So, the D and B matrices are extracted directly. From the at this stage known observability and controllability matrices. Yeah, because in our example, L was equal to 2. Then we calculate O2. And we know that this one is D over A, like this. Then the upper part here is D, simply. The M first rows, you can pick out the D matrix. And from the known controllability matrix, C3, because J is 3 in this example, B, AB, A square B, and then the R first columns here gives us the B matrix, simply as this. What about A? So under these remarks, A is calculated from this one. You see here we have an equation. And A is unknown in this equation. Before closing this lecture, let me show you how we can find A by solving this formula. In this formula, we know the left-hand side is Hankel matrix. And we at this stage, from singular value decomposition, we know O and C. So they can simply multiply from left by the inverse of OL and from right by the inverse of C. Then you have A alone here. But remember, OL is a rectangular matrix. Not always a square and invertible. And this controllability matrix is a rectangular matrix, not always square. So, what we do is to normalize. We know that this one is rectangular, but if we multiply with the transpose of OL from left and multiply with the transpose of C from right, we normalize and we obtain OL transpose H given L times CJ transpose. This one is then equal to OL transpose times OL times A EJ transpose. Here, this one will be square. N by N where? Same with this one. Will be N by N and square. And since we have calculated the observability and controllability matrix with rank N, those matrices are invertible. Now we can multiply, solve this one, multiply from left by the inverse of O transpose O, and from right by the inverse of this one. We find an estimate of A. We can use an hat in order to indicate estimates. Very often I omit this. Now the inverse of this one times this one. Like this, inverse times all this. The J transpose here, and multiply from right with the inverse of this one. Yeah, this is a formula for A. The open key here at this stage is more details about the singular value decomposition. And I will do this one next week. And remember, all this with some more details also is described in lecture notes, chapter 225. And there also is an exercise 1, with numbers. Thank you.